Hello, can you hear me all? Okay, I hope you all can hear me. But some people say that they can't hear me. I cannot hear you. You can unmute your all and give the feedback. Because I see some messages that somebody can't hear me. Please check your settings because the others say that they can hear me.
Yes, I can hear you.
Does it? You have sent that you have said that you can't hear me. Have you checked your mic?
Sir, now I can hear you, sir. Earlier I can't, now I can.
Okay, sure. Right, no problem. Okay, shall we start now then? There are about 16 participants. Okay, I think we can go ahead with our continuation of the lesson. Okay, let me share you my screen now. Okay, is it clear, the diagram? Is it clear, the diagram, that one we have stopped in the last week? Yeah, okay. So we have the three layers in the crust. Three layers in the crust, that is core, mantle, and core. Crust, mantle, and core. The crust is of two type, right? The crust is of two type. Then we divided it into three layers again, depending on the rheological properties or the mechanical properties. Lithosphere, asthenosphere, and mesosphere. Okay. So the lithosphere is the litho part. So what do you mean by litho? Litho means the rocky part, because the crust itself is made of rocks, and then the upper part of the mantle, the most upper part of the mantle, is also sort of solid. So therefore, we call that litho. Litho means rock. Okay, litho means in Greek, it means rocks. So therefore, we may consider it as lithosphere. So that is the solid part of the earth. And if you see the dimensions, the crust is almost like maximum up to 75 to 100 kilometers, but in average it is 30 to 40 kilometers. Okay, not everywhere, but like places like Himalayas, it's thick. So we will see why these places are thick later on. And the oceanic part of the crust, that is oceanic crust, you can see it here. It's about 7 kilometer in average thickness. 7 kilometer thickness, which is around the oceanic part. And if you see the core mantle boundary, it's more than 100 meters. It can extend up to 350 in some places, which we call the mohoic discontinuity. So we will come to that later on about the details for the moho. and the distance from the surface to the next layer, that is the core, is about outer core. Okay, outer core, it's about 2883. It's here, 2883, like. Then to the center of the earth, that means the interior, the innermost part of the inner core, the distance, or in other words, the radius, right? The radius is 6371. 6371. That means the radius of the earth. That is the actual measured amount. These distances have been measured using seismic waves, or in other words, earthquake waves. Okay, the waves that are produced in an earthquake are called seismic waves. So these seismic waves we can artificially generate. So there are such instruments. So once you generate such POS waves, or in seismic waves, there are two types: P waves and S waves. Okay, so they go to the interior of the earth, and based on their velocities, we can measure the distances they have traveled. So by that, the scientists have measured these lengths, or the distances from the surface. Okay, so uh, before going to more details, let me give you another explanation. Just a minute. Sorry, I can't find that document. Sorry, I don't get that image. Let me check again. Sorry, it's not opening anyway. So let us continue with the presentation with the same diagram that we have been discussing. Uh, can anybody tell me that this is okay? I mean, the clearly presented, clearly you can see the diagram.
Yes, sir.
Hello.
We can
Is
see
it
clearly.
the slide? Can you see clearly? Because I have some sort of interruption here.
Yes.
Is that fine?
No, sir. I can see very well. I can see. Fine, fine, fine.
Okay. Right. So let me continue then. Okay. So these are the layers of the Earth, and when we go to the compositions of these layers, as I mentioned before, lithosphere is a strong rocky layer. It can even go up to 100 kilometers at very extreme places only, and which causes the plates to be formed. Okay, the reason is this is the rocky part, the part which is composed of rocks, mainly rocks. Actually, other parts also contain rocks, but not as solid as this much, the lithosphere. And then the the second layer below the rocky part of the Earth. So this asthenosphere is very hot. So this asthenosphere is very hot. So actually, it is very hot, and the magma is generated there, right? And also rigid, but not as rigid as the crust. So therefore, there is possibility for this asthenosphere to move the plates above it, right? Because the lithosphere is on top of the asthenosphere. So because the asthenosphere is a little bit weaker, it has sort of the property of flowing property, right? It's like a gel, or like a jelly even, right? So it has, I mean, it is movable. So therefore, once very high temperatures are present, it can cause the overlying plates, or the overlying lithospheric parts to be moved. So therefore it makes as a driving force for I mean, it contributes as a driving force for these plates to be moved. And then what you have is the mesosphere, which is also hot, but it's very rigid, very strong. It is not like the asthenosphere. It's very strong. Okay, because it is compressed. It's compressed due to the high pressure. You know. Hello. Yes. Anything unclear? Okay, so mesosphere is beneath the asthenosphere. Okay, so asthenosphere, as I mentioned before, it's a weak ductile layer. So what do you mean by ductile? Ductile means it can easily be deformed, right? Deformation, deformation means changing the shape. So being it's weak, it's like a gel, as I mentioned before. It has the flowing ability, but it's not like a liquid. Okay, it's not a total liquid, but not a total solid as well. It's a semi-solid type of a layer. And the mantle uh, lies beneath the lithosphere, and therefore this asthenosphere can deform, right? It can deform, uh, and it can accommodate the motions of the overlying plates, right? That means when the plates are moving, it can facilitate the plates to be moved uh, in different directions because of its ability to deformation, or in other words, being ductile. And then what you have is the mesosphere. It's solid, and I mean it's very compressed, and it can continue up to 2,900 kilometer in depth. After that, you have the parts of the core. So for these two, we don't specifically term them with a sphere or anything. But as you know, the innermost sphere is I mean the inner core. That spherical part is composed of solid iron. Okay, and then outer core is liquid iron. Uh, it is totally uh, metallic, right? It does not contain any silicates because the mantle and the crust contain silicate parts. Okay, so we will learn about these things under minerals. So the silicates are composing the crust and the mantle, whereas the core is entirely of metallic. Okay, in metals, iron or nickel. Right. So we will first see the core, uh, the some additional features of the core. It has taken about 100 million years to form the core during the Earth's accretion. So I think you can remember at the very beginning, the Earth was just a simple mass which did not have any this sort of layering. So the layering started when the chemical differentiation started, right? So first to form was the core. The core formed very beginning because the heavier ones sank from this magma ocean down. Okay, so these materials were sinking downwards towards the central part. So which composed the core, and the process has taken place within a time span of about 100 million years time. So about 100 million years later, the Earth's core formation was completed, and then the rest of the part means the remaining section of the Earth except core. That means entirely silicate part, right? Silicate and the other mineral part, right? So that started to form. That formation also took some time, but the core formation was pretty quick. 100 million years means in geologically it's a quick time. It's not a very long period. Although in our normal life, 100 million years is a very very long period. Okay, but geologically it's a short time span. So the heavy elements, including the metal iron, melted iron, because this is a high temperature, and also the pressure is also very high. Therefore, melting points are very different than the normal melting points that we observe on the Earth's surface. So these metallic particles sank down to form the core, and the inner part is mainly solid due to tremendous pressure. As you know, very very uh, large column of rocks are overlying. Therefore the pressure is very large. So you learned it's about 6,307 kilometers, right? 71 kilometers, right, from the surface to the core. So therefore uh, they are very very robust, they are very solid. And if you consider the mass, the it's about one third of the Earth's mass, right, the core. And because of this metallic iron is there, and also the Earth is rotating and moving, and even the core, liquid core is moving because it is liquid, so it has the ability to move even under high pressure. It controls the magnetic field because it can generate a magnetic field around the Earth uh, by this iron. So therefore, the generation of the Earth's magnetic field is mainly caused by this uh, Earth's core. And then the next layer is the mantle, the Earth's mantle, and which is the layer beneath the crust. The layer beneath the crust, that means this part. Okay, so this is the mantle, and this part is the mantle section. Mm, and it's a containing some rocks, because I mentioned that this is also rocky part. It contains denser material, right? Denser material. That means, in terms of density, the materials are heavier than the crustal rocks. So they are called peridotites. So this is the peridotite, which is a highly magnesium-rich material. Okay, iron is also there, of course, but the magnesium is the dominant element which composes the minerals in this part. Okay, so peridotite is a rock type. Actually, it's composed of magnesium-rich olivine, right? Olivine, gemologically people call olivine peridot. So this peridot means it's actually the host rock type. It's not the mineral, although we call it a gemstone. It's a rock type, because most of the peridotites are more than 90% olivine. So that rock is called dunite, but in gem field people call it peridot, the mineral itself, right? So anyway, the rock type is peridotite, which is mainly composed of olivine plus some minerals like pyroxenes, right? There are types of pyroxenes. We will learn about the minerals later on, the classification of minerals later on. And these are also silicates, but iron and magnesium rich silicates. Okay, it was disconnected, so I'm sharing again. Is that fine? Right. The mantle part is composed of uh, iron and magnesium rich minerals. So that is what you call the peridotite. But the important feature here in the mantle is the mantle forms convective currents. What is convective currents? Convective currents mean it's like something like you are boiling some pot of water, right? If you boil some water, what is happening? And if you put some ink into the water, you will see some ink particles are moving upward with the heat flow, right? That is what you call the convection, convective heat transformation. So that I'm sorry, it seems the internet connection is not stable. Hope you are getting it now. Mantle convection, okay? The mantle convection is there in the mantle, so which causes the material to flow, right, within the Earth's mantle. So this is the reason for melting of these materials. For example, here in this region, there is intense melting. So that is the region where the highest amount of magma is generated, because although the mantle is a semi-solid material, as I mentioned before, the asthenosphere, it's sort of having this deformation feature or ductile feature. You can see some melting also going on in this region. Okay, the melting is also going on this region, and which cause the materials to uh, flow upward as magma, right? So that is another thing happen in this mantle region. In addition to this mantle convection, so this mantle convection drives very heavily, and it exerts a tremendous force beneath the crustal segment. So here we have the crust, right? So here we have the crust. This part we have the crust, and here we have the crust, and this crust is being pulled by this crust is being pulled by the mantle convection, right, in this region. So therefore, the fragmented crust has a driving force to move around. So therefore, the plate tectonics are acting because of this mantle convection. So driving force for the tectonics is this mantle convection. So mantle convection is very important because they are dragging the plates, they are dragging the crustal sections, the segments or fragments in different directions. Okay, different directions. So therefore, they have this ability to uh, move, have the ability to move because of that reason. Okay, right. So the other part, the next part is the crust. So we have now discussed about the core, then the mantle, and the final part is the crust. Uh, the most closest part, that means where we are standing on now. It is a place where we are standing on. Okay. So as I mentioned before, the crust is of two parts. One is the oceanic crust. Uh, One is the oceanic crust. This is oceanic crust. Uh, just a minute, please. Okay, right. The crust has two parts: oceanic crust and the continental crust. The oceanic crust, as I mentioned, it is not very much thick. It's thin, right? So it's like five. In some places, it's 5 kilometers. Some places, it's in average 7 kilometers. But in places like Mariana Trench, in the Pacific Ocean, the Mariana Trench is the deepest place in the crust, the oceanic crust, that can extend up to about 12 kilometers. Okay, and another important feature of this crust is uh, this oceanic crust. The oceanic part of this crust is thicker. The oceanic part of the crust is thicker. So this crust is uh, made of a rock type called basalt, right? This is the rock type which makes the oceanic crust. Basalt is iron and calcium rich uh, rock material, right? So that means minerals like pyroxenes, clinopyroxenes, and uh, plagioclase feldspars are rich in this crustal segment. Okay, so it's very important fact that you consider the crust as a thin layer, crust as a thin layer for with respect to the ocean continental part, but it is denser. So that is the important thing. Density is higher than the normal continental crust because it contains a lot of iron and calcium rich minerals, which are usually uh, of high density compared to other minerals which compose the continental part of the crust, which is the continental part of the crust uh, is mainly composed of less dense rocks, such as granite, for example. Okay, the granite is a lesser dense rock than the basalt. Basalt is nearly 3 grams per cubic centimeter, but the granite is about 2.7 grams per cubic centimeter. But as you know, although the difference is very small, 0.3 grams, as you know, if you consider the plate sizes, the crustal sizes, the kilometer scales, right? This matters. And also it is much thicker than the oceanic crust, but as you know, since it is less dense than the oceanic crust, it always tries to keep on the top part of the levels. For example, if you have a place where these two crusts are meeting together, right, like a marginal place, continental marginal place, like a place like here, okay, what happens is oceanic crust, being its denser, always tries to sink beneath the continental part, right? So beneath the continental crust, oceanic crust always tries to sink down, okay, it always tries to sink down. So that is what you call the subduction. So this subduction always happens at these type of marginal places. So these are called continental marginal, oceanic continental margins, right? So uh, that is another process that we are talking about uh, under Earth's processes, right? We haven't still started Earth's processes yet, but we are just talking about the structures of the Earth only. So we will talk about the Earth's processes later on, plate motions and all. Remember always, if continental crust meets continental crust and oceanic crust meets together, oceanic crust sink down into the mantle even, right? So this goes deeper and deeper up to the mantle levels, and there may after the reaching the mantle level, there are some other processes take place, and some repulsions are also taking place during that type of subduction processes. So we will talk about those processes later on. But for the time being, you just remember that this is a denser layer than the crustal layer. Okay, so it can range up to 70 kilometers, as I mentioned before. 70 kilometers means places like Himalayas, right? Because they can create mountains like here when the plates are colliding each other, right? Especially if this part is also a continental plate, then there is no way for the subduction to happen because both are of same density. In that case, what happens is they just compress each other towards high elevations, making a mountain like feature like here, right? So then this part becomes very thick uh, compared to the normal crustal thickness, and these are the places where mountain belts are generated, like Himalayas, alpine mountains. All these are results of crustal collisions. So that's why the crustal thickness is high in such regions. Right. So do you have any question regarding these the structures, Earth structure or composition, chemical composition, and also the rheological composition? Is there any question? No questions? If no questions, we can continue. Uh, I hope you got it clear. But anyway, if you have any question, please let me know. And also don't forget to put your name and number in the chat box, okay? For registration purposes, for the attendance, right? Please put your name and your number in the chat box. Right. So now, shall we move to the Earth's processes? Okay, Earth's processes. Earth's processes. For Earth's processes, we have to consider the mainly plate tectonics, right? Mainly plate tectonics, because we are considering the continental plates and oceanic plates, continental plates and oceanic plates, right? So these are important because, as you know, our crust is made of some fragments, right? So all these crustal sections, although we consider it as a sphere, right? It's not a continuous sphere. It's something like this. It's fragmented. So it's fragmented like this, making different lithospheric parts. Litho means the rocks, as I mentioned. So we call them lithospheric plates because it contains crust as well as little part of the uppermost mantle. That means the lithosphere. So this lithospheric part makes all these plates. So these plates are composed of these lithosphere, either continental or oceanic, right? So oceanic part is when the fragmentation is there, we call them oceanic plates. When the continental part is there as fragmented, we call it continental plates. So these continental plates and oceanic plates are moving as a result of mantle convection, right? So we mentioned about the mantle convection. So mantle convection is heat flow, right? Mantle heat flow, actual material flowing, right? So these materials are flowing like this, okay, from bottom to top. It's not just flowing; it exerts a tremendous uh, pressure and a force here, right? So once you have the convection force here, flow here, it drags this plate in this direction, right? It drags the plate in this direction, and at the same time there can be convection cells in the opposite direction, right? Like this. If you have convection cell, we call them convection cells for these areas because these are localized convective heat flow regions. So this type of heat flow cells are there. So if you have a heat flow cell like here clockwise, then your plate is dragged or moved in this direction, okay? And because of this direction is opposite, anti-clockwise. If your plate is being exerted this type of a convective cell, then your plate is dragged on the opposite direction. So what happens? One plate is moving. Suppose this is the plate, and another plate is here. So one plate is moving leftward, the other plate is moving rightward. So what has happened there? So there will be some space, extra space generated in this region. Okay. So once you have this extra space generated, uh, the underlying mantle I mentioned in this type of the deep regions, always melting is taking place, right? So remember, I mentioned about the melting, right? This region, this part. So one convective cell is here, another convective cell is there, right? So this drags the slab in this direction, and this force or this cell drags the plate on the opposite direction, right? So some empty area is generated this region. So as soon as this empty area is generated, underlying materials like this magma, melting magma, squeezes up into this region, and it can come up to the uh, surface levels. If this is a oceanic plate, then this magma comes up and dump on the oceanic plate, right? Or oceanic flow, right? This magma is dumped on the oceanic flow because of this, as a result of this plate motion, right? Because you are creating a space here, some empty region where low pressure conditions are generated. So therefore high pressure magma which is lying beneath the earth uh, squeezes and comes up to the surface levels. So here the surface level mean the ocean flow. Okay, the ocean flow, you have the magma generated. So this is happening in the mid of an ocean plate, in the mid of an ocean plate, because this is the ocean plate, and so this is maybe the thickness, and it is happening mostly in the middle part, right, middle of an oceanic plate. So therefore we call this region as the mid ocean ridge, because you have magma generated, and they are accumulated, right? So they are accumulated and they make like a bridge, like a mountain, right? In this region, in the ocean floor, you have some magmatic mountains. It's like volcano. It's like a volcano, uh, which you see on the surface, right? So on the surface, you have some volcanoes like here. And similar way, this magma flow causes magmatic materials to dump on the ocean floor, making undersea volcanoes, because this is ocean there. So water is there, but under the water you have volcanoes. So these volcanoes are called undersea volcanoes, or mid-ocean volcanoes. So these mid-ocean volcanoes generate three-dimensionally some ridges, some mountain ridges like here, right? So along this direction, you can have a ridge, you can have a mountain. So because of this ridge is at the middle of the ocean, we call them mid-ocean ridge volcanoes, mid-ocean ridge or mid-ocean ridges simply, mid-ocean ridges. So these mid-ocean ridges are very common in oceanic plates. So these oceanic plates, when they are moved apart by this type of dragging, mid-ocean ridges are formed. So these mid-ocean ridges are one formation of these mid-ocean ridges are one of the main Earth's processes that is taking place with regard to the plate tectonics. Okay, so this plate tectonic is taking place uh, as a result of this driving force by the magma. Okay, driving force by this mantle convection, right? This mantle convection causes the material to melt in this region as well, right? And that melted magma rises upward because it's low density than this denser rocks there. Therefore it comes up to the surface, right? So since this is an oceanic plate, it causes to form ridges in the ocean floor, in the middle of the ocean. So these are called oceanic mid-ocean ridges. These are called mid-ocean ridges. And not only that, some magma which was generated very deep. So very deep means somewhere here, right? Somewhere here, this depth, some 2,700 kilometers even deeper, right? You can see the depth, see this depth, okay? So the some magma, it is the core and the mantle boundary. So this is the boundary, right? Core and mantle boundary. A lot of scientists have found that a lot of melting is taking place in this region as well, right? So this magma, but it has to rise about 2,700 kilometers, unlike the mid-ocean ridge basalt, mid-ocean ridge magma, right? The mid-ocean generating magma is very shallow. It's somewhere here, right? It has to reach only some few tens of kilometers, 100 kilometers maximum, like maybe the upper part of the region. It's here, okay, in this region, right? But compared to that, this deep magma has to rise some 2,000 or 3,000 kilometers upward. So it is not happening very frequently. So it happens very rarely, right? So this type of magma flow can also happen. We call this type of magma flow as mantle plumes. See, these are the mantle plumes. It takes very long periods of time to come up, right? So therefore you never see these type of magma flows in anybody's lifespan, right? Because for this type of magma flow, it takes about 400 million years to come up, right? To come up to this level, right? It takes about 400 million years. So once in a 400 million years time, this core mantle boundary magma generated in this region comes up as a mantle plume, right? We call it a plume or mantle plume because this plume is coming through the mantle, right? Co-mantle boundary. Right. So this type of magmas are very strong and they are very hot compared to normal magma. Right, 5 6 times, maybe 5 6 times greater in temperature, right, than the normal magma that you expect to have in this region, in a mid-ocean ridge, right? So therefore, this magma has the ability to uh, bombard on the Earth's crust and put into pieces of the earth crust, right? Earth's crust is further fragmented into tiny pieces, right? Some continents become very small fragmented shapes due to this mantle magma, sorry, this core-mantle magma, right? It's very stronger than the normal magma that is we see in day-to-day life, right? Mid-ocean magmas we can see every day. Even now, this moment, there are magma generation. But that magma is also very hot, you know. It's about 1000 degrees Celsius, more than that, 1200 or so. But compared to that, this particular magma that is coming from the core mantle boundary is very hot, right? Like 5000 degrees Celsius, like. So being it's very hot, and also being it's very strong because it comes as a very huge patch, or very big mass. It hits the uh, earth's crust and fragment it into pieces. So that means the whole earth can be distorted by this type of plume, right? That happens once in 400 million years. So we will come to that later on with respect to continental and continent or the we call it supercontinent formation. Later on we will discuss about that. Actually this mantle plume makes huge continents to break, right? We call supercontinent to break, right? Some combinations of continents are called supercontinents, and even these supercontinents, you know, size of a continent is very big, right? So then what would be the size of a supercontinent, right? To break the supercontinent, you need a huge force. So that force is given by mantle plumes. So that happens in every once in 400 million years or 300 to 400 million years time. We will come to that under supercontinent formation later on, because that is also a part of the Earth's processes related to these internal dynamics of the Earth, right? So day-to-day life, what we expect is this ocean ridge formation by the magma flow, and also no, sorry, the normal volcanic eruption. The normal volcanic eruption happens because of this subduction. This oceanic plate is subducting beneath the continental plate, and since it is moving against the continental plate in this region, huge frictional force is generated. So friction is very large here, very intense in this region. So that friction causes heat generation. So as you know, if you rub your hands together, you can feel some hot feature, right? Some temperature, some increase in temperature there. That means heat generation. So if you consider rubbing some plates like some thousands of kilometer big, so you can imagine how much heat can be generated there, right? That heat itself can cause these continental materials to be melted in this region, right? So this heat can melt this material and generate magma. So that magma is coming up and dumped onto the Earth's surface as a volcano, right? So that's how we get volcanoes on our continents. So volcanoes on the ocean is directly resulting uh, by the mantle convection, but the volcanoes in the continental part is mainly related with the heat generated by subduction of plates, right? So that has that feature in the interiors of the continents, like the places like in this region. For example, this is the extension of the continent, right? So in these regions also you can have some volcanoes. So you can see volcanoes in these parts as well. So we will encounter this type of situations as well, because you don't see any oceanic crust surrounding, right? There is no oceanic crust in this region, but still you have a volcano. This can happen actually because of extensional forces, which causes these continents to fracture, right? So when extensional forces are applying, so there is possibility for extensional forces to apply. So we will talk about these things later on. And this region, some low pressure or ruptures are built, therefore low pressure conditions are generated. So into these low pressure regions, from deep interior, some magma can flow and come up as a volcano, right? So these type of volcanoes are also generated, and these are called rift volcanoes. We call them rift volcanoes. So because these fractures are called rifts, okay? It's, these fractures are called rifts. So these rifts are formed because of extensional forces. So therefore, these volcanoes we can name as rift volcanoes. But these volcanoes, which are formed at a subduction zone like here, are termed as subduction zone volcanoes. Subduction zone volcanoes. These are rift volcanoes. So these are the main processes that you can observe superficially even. As a result of these plate motions. So these plate motions, we in general term, you can collectively term as plate tectonics. Okay, so these plate tectonics, the main driving force is the mantle convection. So you have to always remember that if this mantle convection is not there, right? So this boiling feature is not there in the mantle, you don't see these plate motions, and also you might not see any active feature on surface of the earth. So that's why some planets are very inactive. They don't have these plate motions, or they don't have these mantle convections or whatever similar to our earth's processes, right? So therefore they don't have any active volcanoes or such type of features, right? Of course some planets do have, but some planets did have this type of ones in the past, and now they are inactive, right? Even our planet can be inactive sometime later, right? So anyway, we don't know, we never know when it happens, but until that time these processes are continuing. Okay, so these are the main earth's processes, and if we are to learn in detail about the plate tectonics, it's better that we get to know about how these plate tectonics were introduced as well, because this was introduced by a German scientist called Wegener, Alfred Wegener. He invented this one just by looking at some evidences on the Earth's surface. For example, he was curious about the plants and animals distribution among the continents. So as you know, the some part of Africa, for example, if I draw Africa is like this, and some part of India like here, right? So Alfred Wegener noticed that some similar type of flora and similar type of fauna can be found in both of these continents, but in regions like here, for example, in the eastern part of the Africa and western part of the India, for example. And similar situations were there in the western part of the Africa and eastern part of South America, right? So he was thinking and studying more and more about this similar behavior or the similar distribution of same type of materials with respect to the life. He found later on that this could have been uh, caused by all these continents were some time ago together, right? So he thought these continents could have been together some time ago. Otherwise, it's very difficult for this for flora and fauna uh, to uh, to cross these huge oceans like Atlantic and other or Pacific like oceans to come into that those the other continents, right? But still, uh, in those continents also the distribution was very characteristic. So he was able to later on by this evidence to fit these continents together. So the current configuration of the Earth, he reconstructed backwards by mapping of these animal and plant species, right? So then they came out, he came out to a configuration like a puzzle, right? Jigsaw puzzle. That means you see one continent is there which is fitting with another one, right? So you can fit another one there into the uh, area in between. So likewise, like you are fitting pieces of a puzzle, right? So this concept was introduced at that time by introducing a fossil map, because he researched about fossils. By the fossils only he understood that similar type of species were distributed in uh, different continental parts, and then later on he was able to uh, connect these continental parts, and he was successfully reconstructed these continents, these continents, and he found that they were together at that time. Okay, they were together that time, right? So that is the uh, birth of the theory of plate tectonics, which we term as continental drift. So there was a understanding that these continents initially were like this, but later on, because of drifting, that means like floating, they were move apart into a configuration like what we have today, right? Originally, the continents were together. So this type of reconstruction was made by Alfred Wegener, and he later on explained that this could have been a reason uh, due to this continental drift. So this continental drift means the plate tectonics that we are referring now, right? So this is the first concept that people learned about the continental drift, and it related with the uh, Earth's plate tectonics or Earth's motions of these fragments, right? So this was a very important finding at that time, which actually could explain a lot of Earth's processes afterwards. Otherwise, scientists were in a question how to explain some Earth's processes. Okay, so therefore, uh, this was a very breakthrough at that time in terms of biology as well as geology, physics, and everything in most of the fields, because this could explain a lot of activities or a lot of processes which was unexplained at that time on the Earth. Okay, so this continental drift means parts of the continents. That means some fragments of the continents are drifting. They are moving, right? They are moving. For example, this Indian part. For example, here you have the Indian part. This can move this way, right? And the African part can move this way, so that you have a separation here, right? You have separation here, and this Antarctica part moves this way. If you consider the today's configuration of the Earth, right? Australia has moved further eastward like this, and South America has moved like that, right? So this is how the Earth has now come into some kind of a shape. So this is because of continental drift, And what is happening, or what is initiation for this drifting is actually at the very beginning, a force which is called the mantle plume that I mentioned before hits this huge continent, because originally these continents were together, right? So this is a collection of the continents. That is what you call a supercontinent. So actually this is a not few continents, but it's a single continent. So actually this has become a one part of a continent, like this huge continent. You can see the collection of continents. That is what you call a supercontinent. So this supercontinent was together at that time, some time ago, right? But later on, what happened? What was happening there was this type of a mantle plume came up and hit this continent in a region like here, right? This mantle plume was hit in a middle part of this supercontinent, and it was broken. It was broken, and these fragments were moving here and there, right? That is what happened at some 400 million years ago, actually, at last. So that's why I mentioned that these mantle plumes are coming once in 400 years. Like people have found with evidence that every 400 years time a supercontinent is formed like this. And soon after formation, a mantle plume is also recycling every 400 million years time, and it hits this supercontinent and fragments it, and it fragments and moves everywhere, and the earth becomes in earth forms into a different shape, right? So since it has taken about 300 million years now, after the last mantle plume, uh, now we have come to a like 300 million years time, right? Lapsed time. So another 100 million years later, our continents will shape up into another supercontinent, different supercontinent of a separate shape, not the same thing, maybe. And we will be hit with another mantle plume after 100 million years later, right? And then again, we will be drifting towards a different shape. So if we are there at the 100 million years later, we will see a mantle plume hit our planet. Okay, so that happens actually. So the last mantle plume hit was the Hawaiian mantle plume. The Hawaiian Islands, actually, uh, the place where the Hawaiian Islands are located now, that is the place where the mantle plume was hit. Although now that place is a ocean, Pacific Ocean, but at that time it was something like this region, right? Central part of this region, right? So Hawaiian Islands was there. The islands were formed later on as a result of this mantle plume. Islands formed because of this type of volcanic activities, right? A chain of islands were formed, and that composition of these rocks are different from the composition of the rocks we have in this type of mid-ocean ridges, like, okay. So that's why we characterize this magma is different from the normal magma that you have in mid-ocean ridges. Okay, so Hawaiian Islands are characteristic in chemistry also, in terms of their rock chemistry. Okay, so those are the remnants of this mantle plume uh, now existing, right? Previously it was a center of a supercontinent like this, right? So actually this supercontinent was there at that time, and the configuration was exactly same as the picture that you are looking at now, right? This was called Gondwana, right? It was called Gondwana supercontinent, right? So this supercontinent formation is taking place in every 400 billion years time, right? So this is actually the Gondwana, but before Gondwana there has been another supercontinent. That's what you call Rodinia. The name of that supercontinent is Rodinia. Okay, so that supercontinent was existing about 400 million years, 700 million years ago. That means just before 3 to 400 million years before the Gondwana, because Gondwana was there about 500 million years ago, uh, for 400 to 500 million years ago. And before Gondwana, the Rodinia was there. So that means nearly 800 million years ago from today, right? Rodinia was there as a supercontinent, and this supercontinent was hit by a mantle plume from the central part, and it was separated. So this separation caused the today's fragments of Antarctica, Australia, Amazonia. Amazonia means the European part, Baltica, Africa. Like fragments were also there, but in different shapes, right? Not in a current shape. And these fragments were moving as a result of this hitting of the mantle plume, and the Rodinia was dispersed. We call it dispersal. And after 300 or 400 million years later, after this mantle plume hit this Rodinia, all these separated fragments were collected to a shape like this, right? To collected to a shape like this, which we termed as Gondwana. So Rodinia dispersed after mantle plume hit, and it formed into a shape which we termed as Gondwana, right? So this Gondwana was also existed for some time, and it was also broken, right? We call breakup of supercontinents, right? Breakup of supercontinents by mantle plumes, and after that they amalgamate together. These broken parts amalgamate. For example, the Rodinia was broken up about 700 million years ago, and it was amalgamated to form Gondwana at about 550 million years ago. So one supercontinent forms another supercontinent. For that purpose, it takes about 400 million years time. So at every 400 million years time, uh, there will be again a mantle plume as well. So that will hit the formed supercontinent, and it will break into pieces and disperse everywhere. And these dispersals are will cause again a supercontinent, another future supercontinent to form after another 300 to 400 million years later. Even now, our continents are also moving, right? Even we are now, even at this point, moving towards northeast side, towards India, right? So these plates are moving, right? So that is the continuation of this supercontinent formation process. Sometime later, some 100 million years later, we will be configured into a different shape, probably like this, so a different shape, one of these shapes, because all these continents should be fit into uh, one supercontinent, right? So that is happening. So anyway, this Gondwana was also broken as a result of a supercontinent, as a result of a mantle plume hitting. So that's what we term as the Hawaiian mantle plume that made this Gondwana to fragment. So these fragmentation parts broken into different pieces. For example, this was the 550 million years ago, the shape, the Gondwana. Once it was broken, it fragmented. It fragmented, and these fragments were in this shape about 225 million years ago from now. That means after nearly 225 million years after this Gondwana breaking, right? So 225 million years has taken place for this continents to come into a shape like this. Okay, from here to here, 225 million years it has taken. And then after another 25 million years later, it was like this. Okay, and then after 135 million, I mean, after another some tens of million years later, it was like this. That means to 135 million years ago. And when it comes to 65 million years ago from now, the shape of the world was like this. Okay, and now after another 65 million years lapse, present day, this is today. Okay, this is today, and after 65 million years time from this configuration, the Earth is now in a shape like what we have today, right? So when it goes another 100 million years time, so all these continents will be again together, right? Somehow there it will be a giant or gigantic supercontinent forming all these continents together, right? We don't know which shape it will be, but it will be like this. And then maybe most probably 100 or 200 million years later, or 100, 150 million years later, there will be a mantle plume again. It will hit this supercontinent just formed, and it will breaks into pieces again, right? It will break into pieces again. So this will be happening as a cycle, right? This will be happening as a cycle. That is this particular cycle we call uh, the supercontinent cycle, right? The supercontinent cycle uh, means this type of a cyclic process, right? So it's a very very common situation for the Earth, because Earth has been formed and under such dynamic forces which makes the shape of the Earth always changing, and every 400 million years time you will have a supercontinent like feature, right? So this is the situation which is happening on the lithosphere, right? So all these processes are taking place uh, in the lithosphere, because these continental plates and oceanic plates are part of the lithosphere, which are moving here and there as a result of mantle convection, and also as a result of mantle plumes, right? Mantle convection just make these plates to move only, and they accumulate or they combine each other to a bigger continental configuration like this, and then it is broken again by a mantle plume like this. So this is happening cyclically in a cyclic manner in the Earth's interior. Okay, so is it clear this supercontinental cycle? This is a very important process which you have to understand when you are to learn about the Earth. The tectonics, we call tectonics of the Earth, right? This is the tectonics of the Earth. Is it clear? Any questions?
Yes, sir.
Yeah.
So I have a question.
Yeah.
On the top right hand side picture, the Triassic period,
Uh-huh.
200 million years ago, the
Okay.
Gondwana land in that picture, and the Gondwana that we discussed about in the other picture, 550, those are two different supercontinents, right?
Actually,
The Gondwana and Gondwana land
yeah,
are two
actually,
different.
yeah, yeah, it's a good question. The Gondwana supercontinent is depicted by this picture. Okay, Gondwana supercontinent. Actually, this Gondwana supercontinent, after hitting the mantle plume, it was broken into two segments. Those two segments were called uh, uh, the two segments were called Laurasia, this one, and the Gondwana land, right? Actually, you are correct. This is a separate continent. I mean, separate. It's in a process of breaking of this supercontinent, main Gondwana. This is the main Gondwana supercontinent, which was broken into two parts. One was the northern part was called Laurasia, and the southern part was termed as Gondwana land, right? You are right. Yeah, that was the thing happened at about that 200 million years ago. But at the time of 225 million years ago or 300 million years ago, this separation was not complete, right? That separation was not complete. Only one segment was here. One part of this Gondwana land was here, but it was not the complete Gondwana land, and also not the complete Laurasia, but a bigger continent was there uh, soon after the breaking, soon after this mantle plume hitting. So that since that part was also considerably bigger, people termed it as a separate continent called Pangaea, right? So this Pangaea was broken actually into two parts. One was Laurasia, and the remaining part, the rest of the Pangaea part accumulated with the remaining section. These two were together, formed together, and termed as Gondwana land. That's how it became into two fragments. Is it clear?
Yes, sir. Clear. Thank you.
Yeah. Okay. Right. So, any more questions? If you have any more questions, you can pose now, or otherwise, we will continue. Right. So this is supercontinental cycle, right? So you can learn more about the supercontinental cycles in the Wikipedia as well, right? Because the general descriptions are there in the Wikipedia also. So you can get more details about that. Actually, there are a lot of data. I mean, the research is going on this topic as well, even now. Even our rocks, our Sri Lankan rocks are part of the Gondwana. Uh, actually, this Gondwana was of two sections, right? We term it as East Gondwana. I did not go into that detail. East Gondwana and West Gondwana. Okay, East Gondwana and West Gondwana. After Rodnia breaking, there were two parts. These two parts collided together and formed the main Gondwana. Right. Our Sri Lankan part is at the East Gondwana side. Right, at the East Gondwana side, somewhere here. Okay, so we have still the evidence for Gondwana because our rocks are rocks have undergone metamorphism at 550 MA, right? It has been exactly determined the age of our rocks, metamorphic rocks. So this 550 means the Gondwana formation time. So we separate zircons from our rocks, and these zircons are subjected to isotopic dating, and they give exactly 550 million years of age, right? So that indicates we were part of this Gondwana during this formation. And similar ages are found in other fragments as well, so that we can correlate those other segments of the rocks as well. Okay.
So can I ask some question?
Yeah, sure.
So this due to this supercontinent the cycling,
Mm-hmm.
are there any records about like whether the size of the continent has been reduced? Like I mean the ocean part has become more and
Yeah. That's a very good question. Yes, I did not talk that aspect in much detail, but I forgot to mention that this supercontinent formation is a result of closing of oceans, closure of oceans as well as opening of oceans, right? Closing of oceans as well as opening of oceans. What do you mean by that? Right here, you have suppose you have here the Rodinia supercontinent, right? So this as I mentioned, it was hit by a mantle plume. So then what happens? These are fragmented, right? Suppose this big continental part is fragmented, and this part fragmented then move somewhere in a direction like that, and the other part should move some other direction like this. Then what happens to this central region, this part? These parts get an opening, right? Actually, this opening part becomes into an ocean later on. So this is a birth of a future ocean. This is a birth of a future ocean. So this is what we call the opening of oceans. Opening of ocean. So when this particular continental fragment move in this direction, what happens to this already existing ocean here? There is an ocean here. So when this moves towards the other continent, if this is not moving that direction, right? Probably it might be moving this way or some other direction, but anyway, this is moving, right? So this moves, and what happens to this already existing ocean? For example, even this part, right? Because of these continental movements, this ocean part becomes narrow and narrow, right? Gradually it becomes narrow and narrow, and finally it gets closed, and because of this attachment they get closed, right? So that means disappearance of some existing oceans happen. So opening of oceans as well as closure of oceans. Actually, these ocean basins are forming and ocean basins are closed. This happens as a result of this one. So volume wise, there can be differences into oceans, the amounts of oceans and amounts of continents even, because melting is also taking place. So that melting causes the existing continents to reduce in their masses, and that happens. But actually, you can't destroy the mass. Mass conservation is there. So this this is compensated by some another process. For example, uh, all these activities are caused by subduction as well, right? For example, even this collision or moving means one oceanic subduction. For example, if I relate this one, right, this continent, right, if this continent uh, is moving this way, right, for example, you can relate it into a plate motion like this. So one continent is moving and it subducts beneath, so that means you are reducing the mass of this continent, right? But while going down, what's happening here is you are melting this as well, right? You are reducing the mass by subduction. At the same time, you are melting this part and you are getting new magma dumped onto the surface. So losing mass is compensated by this volcanic activity. So likewise, there is a balance. There is a balance happening. So therefore, the total mass of the Earth does not change. So somewhere this mass is preserved in terms of that. So anyway, closing of oceans are happening and opening of new oceans are happening. So for example, you can see here, yeah, it's a very good place to understand here, this section, right? So you have two continents. For example, the African part and the South American part is there, right? They were together, but with the process going on, what happens? These two continents are separating, right? Because of this continental drift, these two are separating. And what happens here now? A new ocean has generated. So this is the birth of a future ocean, right? This is the birth of the future Atlantic Ocean, right? Now you have the Atlantic Ocean here. Previously it was not there, right? So now we have an opening of ocean. At the same time, the previously existing ocean was here. For example, this one here. This is called a Paleo-Pacific Ocean. Actually, this ocean was the ocean before the current Pacific Ocean. So therefore, we call it Paleo-Pacific Ocean, not the currently existing Pacific Ocean. So this ocean was somehow closed due to these activities, and later on, a new Pacific Ocean was generated there, right? So now, currently existing Pacific Ocean is a new ocean which was formed after 550 million years ago. So before that, there has been an ocean here, which is called Paleo-Pacific Ocean, right? So likewise, the removal of masses from oceans or continents can happen, but the overall mass will be constant because some compensation process is there somewhere in the earth, right? As a whole, it will be constant. Did I answer your question?
Yes.
Okay, right. So always remember, closure of oceans and opening of oceans are happening as a result of this supercontinental cycle, right? Right, now let's see the current configuration of our planet. So now we are in a shape like this, right? So we are in a situation like this. This is the continental configuration currently we have. So we have oceans and we have continents, right? So as I mentioned before, all these oceans and continents are connected like this. So if you see this, for example, here, right? So if you take this part, take this one. So this is the South American continent, and you have the Pacific Ocean here. So you have the Pacific Ocean at the edge, and you have the continent there. So what is there? It's something like here, right? So if you take this section, you have the Pacific Ocean this side, and you have the South American continent. So this is this equivalent situation, but it is different if you consider uh, this section, right? This part here you have totally continents, because you have one continental fragment here called Europe, and another continental fragment here called Asia, right? Together we call Eurasia, right? You can call Eurasia because it is Europe and Asia together, right? Not Laurasia, right? This is Laurasia. It's a different thing. Anyway, you have one continent there and another continent uh, at the margin of that. It's a different situation. So that means you have a continent here as well, right? Not an ocean, oceanic plate, continental plate and a continental plate together. So it's a different situation. So likewise, such places are there. Anyway, so that's why we can consider our planet into fragmented shape like an eggshell, right? Eggshell, if you fragment, you will see very fragmented behavior. So this is why we term that our crust has divided into plates, both oceanic and continental plates. So the previous example that I took, which was coming from a place like here, where you have the South American section here, plate here, and you have the oceanic plate here, right? You have the oceanic plate here, which is part of the Pacific plate. This is the Pacific Ocean, not the Pacific plate, Pacific Ocean, one segment of that ocean, right? But it's a small plate. We call it Nazca plate, right? So these are different plates are there, and the other situation where you have the Asia, that means Europe and Asia. So you have one plate here, continental plate called Eurasian plate, and the other plate we have uh, Indo-Australian plate, Indian plate or Australian plate. Some people term this part as Indian plate and this part as Australian plate, but this is a single plate. It's called Indo-Australian plate, right? Some margin is now being developed. It's not fixed yet anyway. I mean, only the evidence has found, but not it's completely formed. So therefore, we can still call it Indo-Australian plate. So this is also continent. I mean, this part is continent, and this part is again continent. So continent together. Here, ocean, continent together. So likewise, you have very different plates, tectonic plates. So there are about 12 main plates and some minor plates as well, small plates. For example, here you have in the margin of North America and South America, you have this Caucasus plate, plate called Caucasus plate. That's a very small plate. Okay, and the biggest plate you have, the oceanic plate, is the Pacific plate. This is the Pacific plate, which is the biggest plate, and the Europe is there, Eurasian plate, and the Pacific plate are together. So it's a situation like here, right? So you see this being this is oceanic plate, the Pacific plate, it's heavier than the Eurasian plate because it is continental. So what should happen? Like here, this oceanic part should subduct, right? It should go down, right? So similar thing happens here. This you can see this arrow indicates it moves in this direction, right? Actually these plates are moving in different directions, so you understand it's like you can have a piece of a cloth and four people are dragging from four sides, right? So you can feel the stress that is applied on the cloth when you are dragging, right? So likewise in different directions you have forces, so that means that these plates are subjected to under height stress. In some places it is compressed, right? For example, this region it is compressive forces, but some other places like here you have extension, right? Extensional forces. So likewise there are different forces are acting upon. All these are due to mantle convections, because underlying these plates are the mantle convection cells are there, right? So anyway, being this is an oceanic plate, this Pacific plate is heavier, which subducts beneath Eurasian plate. So it subducts beneath Eurasian plate, causing what kind of features? So it moves downward because of friction. As I mentioned, a lot of heating is there. So a lot of magma is generated as volcanoes. So what happens there in the real situation? Here, there will be a lot of volcanoes. lot of volcanoes coming out. So where is this? This is Japan, right? This is Japan. So that's why you have a lot of volcanoes in Japan because of this subduction. Not only that, being the plate is subducting, it's not a very smooth process, right? It goes like this and comes a little bit up and again goes down, a little bit up, likewise. It's very alternate process. So that causes huge vibrations in this region, a lot of vibrations in this region. So that means a lot of earthquakes can be there. So in Japan, that's the reason why you have a lot of earthquakes because of this plate subduction. It's a huge plate subducting. So entirely the Japan country is located along the margin of the plate. Therefore, it's very vulnerable for earthquakes and volcanoes. But if you consider Sri Lanka, this is Sri Lanka, right? We are in the middle of a plate. We are in the middle of a plate and we are away from a margin. Although this margin, which is being now being formed, still about 3,000, 2,000, more than 2,000 kilometers away, right? 3,000 kilometers away. So we don't have much effect on that. So that means we are stable tectonically still, right? We are on a stable base. Therefore, we don't experience any volcano or any earthquake. That's the reason. But the countries like Japan, every day they are having a volcano, earthquake or a volcanic eruption. Somewhere there is eruption or somewhere there is earthquakes, right? This is very common because of this tectonic movement. That's why I mentioned that even at this particular time period, moment, just at this moment, there can be earthquakes in Japan. There can be volcanoes in Japan. That's the reason. So similar things are happening in the western coast of America as well. You have the uh, the Pacific plate and the American continent, North American continent. But the situation here is a little bit different because you can see the movement direction of this plate is like towards that direction. So it means like you are sliding this plate against the American plate, right? So it's like you are sliding this one, right? So the nature is different. The movement is different. It's not direct subduction, right? It's just rubbing the Pacific plate against the American plate, like so. In the Western California, there are a lot of earthquakes because of this type of motion. Rather than having volcanoes, you have a lot of earthquakes in this region because it's a parallel motion. We call it transform faulting. It's a transform like faulting. Faulting means moving rock layers against one another with respect to one rock layer. uh, they are moving, right? Some displacement is taken, or in other words we call it offset, right? So this Pacific plate is offset to some extent with respect to the North American plate because of this type of motion. So anyway, this Pacific plate being the huge or largest plate, it can move in different direction in different parts, right? It's uh, having different forces active on different segments, right? So like the example that I took before, you have for example, you take a cloth of piece of cloth and from four edges, four people are holding, and these four people can hold it or drag it or pull it in different directions. So the particular cloth gets different forces acting upon at different regions, and one can run even. So then what happens? It's like you are rubbing one Pacific plate against this one, right? It's like shearing motion, like a shearing or tearing, right? So anyway, this type of things are happening in the tectonic movements with respect to the plates. And you can see here this region, this part is the Atlantic Ocean. You know, the Atlantic Ocean. South America is here and Africa is here. In between you have the Atlantic Ocean. So you have one plate here, African plate, and you have a South American plate here, and this part you have North American plate, and this part Eurasian plate. So all these plates are at marginal in the Atlantic Ocean. That's why the Atlantic Ocean basin was formed, because you can see here this plate motion is this direction, and here this motion is that direction, right? So you have motion like here in this place, like you have this direction motion and this direction, opposite direction. So what is happening inside, in between? You are creating a low pressure extensional regions, like the place where you were talking about the example for the extension. So I mentioned that there will be a volcano here, right? There will be a volcano. So similarly, there will be volcano, but being this is an oceanic plate, you have the undersea volcanoes, right? Mid-ocean ridges, as I mentioned. So the same situation is there. The mid-ocean ridges are formed here. Mid-ocean ridges are formed here, right? Because of this motion. So you can see here, there is a country here, a continent here. What is this? This is Iceland. So if you see this one, this mid-ocean ridge continues in the middle of the country, in the middle of the Iceland. So you can see in the middle of the country some volcanoes, some big volcanoes. So in this region, you can see the volcanoes in the ocean, but in the country, you can see the huge volcanoes in Iceland. So you just go to the Google and search the Iceland, then you will see some cities are burnt because of these volcanoes, right? So actually the Iceland will be separated into two sections, two countries. Iceland will become divided, will be divided because of this motion in the near future. Some million years later on, it will be splitted into two, right? So there will be two countries, two continents will be formed. I mean, small fragments of continents will be formed. Iceland will be splitted because of this motion. So there are a lot of mid-ocean ridges because of this one. So we call Atlantic mid-ocean ridge, right? This is continuing. It's a very huge one, very big one. And at the same time, we have the Indian Ocean as well, right? This ridge we call Indian ridge, Southwest Indian ridge, right? So likewise, in the middle of the ocean, you have the mid-ocean ridges, okay? Right. And one more thing. Now, if you go to the African continent, now the Africa, if you go to Africa and Ethiopia, Tanzania region, right? Some region like here, you will see this continent is being split. This continent is being split like this, right? So there are volcanoes generating in this region, because you see this fragment is moving this direction, right? The continental fragment, and this African continent part is moving this direction. So you are creating an extensional force in this region. So this part is already fragmented, already ruptured, right? So being ruptured, you are exposing this part to the mantle, Earth's mantle, because you are rupturing the crust. So this part is exposed to the mantle, and from mantle there are magmatic eruptions. If you go to Ethiopia, you can witness this by your own eyes, right? This is happening. And in the future, what will happen? This African continental part will move this way because of this extension, this way and or this way. And this part will be moving this way, so that this fracture will be more broader. It will become more and more broader. So what will happen finally? This will give rise to another ocean here. So there will be a new ocean generated here, right? So this part will be fragmented and a new ocean will be generated in the future, right? This is very dangerous because this part of the Africa is very thin in the crust, about 5 kilometers. So if you drill 5 kilometers, you can bring a bucket of magma, okay? It's very, very shallow. So that region is very dangerous. We call that part as Afar region. The name of that region is Afar, right? You can check this in the internet, Afar, okay? Afar region. Afar means hotspot region. That means where it's a magma region, okay? All these are the results of plate motions, tectonic plates, right? So This is what is happening in the Earth with respect to the Earth structure, our current Earth's structure, and the tectonic forces acting upon will cause these plates to be moving in different directions. So always remember, they can create oceans, they can create new oceans, as well as they can create they can destroy existing oceans, right? For example, here in the Afar region you are creating a new ocean, but when it comes to this part, the Atlantic part, in the future, right, you are narrowing that part. Gradually it's being narrowed. So that means uh, some closure of the oceans are also taking place. At the same time, some new oceans are also being formed. So that is what you call the as a result of the continental cycles or the supercontinental cycles, right? So we are experiencing it even the present life. Okay, so these are the main tectonic processes. We call them tectonic processes because they are related with the mantle convection forces. Always these mantle convection forces, we term them as the tectonic forces, right? Okay, so do you have any question regarding these sections? Okay, so we can summarize what we learned today. Actually, we learned about the plate boundaries, right? So we learned about types of plate boundaries, but we did not name them actually. But we just mentioned that we had some plates, different plates, right? Due to different forces. For example, mantle convection forces, we have different plates generated, and different tectonic areas are generated because of that. For example, number one here, right? We can summarize all these areas. Number one, what is here? We have a subduction. This is an oceanic plate. This is an oceanic plate. This oceanic plate is subducting downwards, right? And the important thing here is another oceanic plate is here. So another oceanic plate is here. Whatever weak, but being both are oceanic plates, almost same densities are there. But there can be some local variations. So therefore, whatever the heavier one or whatever the weaker one, which is easily deformed, will be subducting, right? So there is possibility for one oceanic plate to subduct beneath another oceanic plate as well. So there also you have the frictional heat generation, and that heat will cause a volcano to form. So this type of plate motion, one plate is moving towards each other, right? So one plate is moving to the other plate's motion direction like this. So this type of places we call convergent plate boundaries, convergent plate boundaries, okay? Convergent plate boundaries. So these are the convergent plate boundaries. And another situation is possible where some parallel motions are there. For example, I mentioned about the Western United States, right? Here, one plate is moving this way and the other plate is moving, for example, in another direction. I mean, obliquely this direction. So that means it's a kind of a parallel motion. It's not collision or even subduction. It's different. So we call it transform faulting. For example, one plate here. In this situation, in this example, it's both oceanic. Okay, this plate is moving this way. So that's why you have this particular uh, this particular oceanic part has shifted or offset, right? You have some offset. We call this offset, some displacement. This displacement is caused by this parallel motion, and this one has moved this direction, right? So it's something like you are moving one plate this way and the other plate that way, like this. So this type of a movement we call transform plate boundary. Transform plate boundary. And then the third one, exactly in this region here. This plate section moves this way and this plate section moves this way. But you can understand that this is the same plate. These are not related with two plates. This is the same plate, just fractured or fragmented or ruptured only, right? Like here, right? So you have one plate ruptured, and because of that, motion is taking place and magma is coming up, right? Like that. So there, what is happening? One place is moving opposite to the other plate's motion direction, right? Like this. So that type of places we call divergent plate boundaries. Okay, divergent plate boundaries, because the plates are moving away from each other. Divergent plate boundaries. And again, you have another situation similar to the situation of number one, where one oceanic plate is moving towards the continental plate, because continental plate is moving this way. You can see it is moving this way, continental plate. Oceanic plate is moving in this direction, right? So what is happening there? That is again convergent. So you have another situation where convergent plate boundary, but in this particular situation, you have both oceanic and continental plates. But at the first instance, you had both oceanic plates. That is also possible. So in the first situation, you have volcanic eruption, and this eruption causes uh, volcanic material dumped on the ocean, and there is possibility for some islands to form, because of this volcanic eruptions, right? Some islands are formed. These are called island arcs. We call them island arcs when there is oceanic uh, uh, convergence, right? Oceanic convergence. If you have oceanic convergence, when you have oceanic continent convergence, still you have the volcanoes formed, but you can understand that that volcano is formed uh, at the part of the continental site, so we call them continental volcanoes or continental arc volcanoes, continental arc volcanoes. This is the same situation where you can see the Andes mountains, right? Chile, the western South America, you can see the Andes mountains there. There you have the oceanic plate and continental plate. So this is a situation similar to that, right? This is an continental volcanic formation, right? So anyway, this region is again convergent plate boundary where magmatism is also taking place very clearly. And there is another possibility I mentioned. You can, if you can remember, interior of the continents, there can be extensional forces, right? So here you have the extensional forces. It's against the compression, right? Extension, right? Tensional forces are acting there. So there, the huge continents can be ruptured because of these extensions. That is what is happening in the South Africa, in Ethiopia, or Tanzania, Kenya region, right? Extensional forces are acting there. Sorry, here, rupturing the African continent, right? So it is interior of the continent. So something like here, interior of a continent, like here, in this situation. Okay, so that type of regions are called rift zones, continental rift zones, because rifting means fracturing or breaking or what do you call fragmentation. Okay, uh, the continental rift zones, we call them such regions, continental rift zone. So these are the all possible types of plate boundaries that you have in the planet, on the Earth's crust, because all these are found on the Earth's crust as plate boundaries as a result of convectional uh, currents, right? Convectional currents, which cause different type of forces to be acting upon the crustal plates. So this is the summary of the Earth's processes that we have been talking about. And I hope you got some idea about the Earth structure as well as the Earth's processes by now, right? So all these processes are very important, and the physical parameters, physical conditions prevailing in these regions are very different from each other, right? The temperature situations, the deformation processes are different. That's why in some regions of these, some special geological conditions are there, and some specific minerals are crystallizing, right? Some regions, even some gem varieties you can see with respect to these one. For example, in this type of subduction zones, right, the rocks undergoing can be subjected to very high pressure regions. So you know there are a lot of carbon in rocks in terms of organic materials, or as well as the graphite like mineralizations. So these can be taken into deep interior, and they can be converted into diamond, right? Carbon can be in a more denser form, which we call diamond, right? It's different from graphite. The structure, crystal structure is different. So therefore, those type of situations are the ones that we term as special geological conditions. So that's why you don't see diamond everywhere, right? Only in some zones you see diamond. Some continents only you see diamond, because at the early history of the earth, these regions have subjected to this type of tectonic activities. In our countries, we have ruby, sapphire, mineral, like gems varieties, because they need some collision environment like this, right? Continental collision. Actually, our region, continent collision, right? Continental collision. Actually, it is not. So yeah, I'm sorry. Number 6 should be there. That is continental collision. For example, one continent is here. You have one continent and another continent. If you have another one here, these two continents are colliding together. So you put that as well. That is continental collision zone, right? So there you have huge temperatures generated, and these high temperature crustal regions are favorable for high aluminium minerals. So high aluminium minerals means corundum, right? Corundum means ruby sapphire, right? Aluminium oxide. They are very dense. So such high temperature conditions are required. Very high temperature conditions are required for such kind of areas to form that sort of gemstone. So that's why we consider that some not only the durability, beauty, and the hardness and all for the gemstones to be, for the minerals to be called gemstones, but they need some genesis, some special conditions at their genesis as well, some special geological conditions as well. Okay, so these are the activities happening on the earth. And as an introduction, I hope you got these points very clearly. And if you have any question, you can pose right now, or even you can send me an email asking, if you have some doubts, right? So do you have any questions? If you have any questions, you can ask now. Otherwise, I think we can stop the class for today, because it's already the time. Yeah, any question? If you have any question, you can ask now. No problem. I can give you 5 minutes.
Sir,
Yeah.
like when it comes to Sri Lanka, like there are no like continental boundaries. Like there is no way to have collusions, isn't it?
Yeah.
So like you said, like the sapphires will form due to that. So,
Yeah.
but
Actually, it's not the present situation. The sapphire ruby that you are collecting now from Ratnapura is a product of continental collision that happened about 550 million years ago. Okay, it's not the
yeah,
present situation. Now we don't have the collisional environment, but if we have collision in the future as a result of this continental cycle, supercontinental cycling, there is possibility for new such gem varieties to form in the future, right? Now what we are getting is the gems which were found, which were formed in rocks about some hundreds of million years ago. That time Sri Lanka was part of the collision zone. As you can remember, we were part of the Gondwana, right? I mentioned that Gondwana was formed as West Gondwana and East Gondwana, two sections. So Sri Lanka was part of the East Gondwana. So this East Gondwana was colliding with, I mean, the continents of East Gondwana was colliding with the continents of Western Gondwana. So there some very high temperature conditions were occurred at that time, about 550 million years ago. I'm talking about now. So that time these gems were formed. So these gems were remaining in rocks, retaining in rocks for that large time span, and the rocks were eroded. So these eroded rocks were dissolving the material, but the corundum like things are very hard, as you know. The gem varieties are very hard to weathering, not like feldspar. Feldspar is easily converted into soil, right? So these are now remained in soil in the low-lying basins because of the erosion. After 500 million years later, that is why it has happened, right? Not the present situation.
Okay, sir.
Yeah,
And also, sir, there's another small question. Like when it comes to diamonds,
yeah,
so you said like it forms in subduction for zones.
yeah.
So apart from subduction zones, is there any other places where you get diamonds, or like only at subduction zones?
No, not only at the subduction zones, but also mantle itself contain carbon. Okay,
Yeah.
mantle, the lower part of the upper mantle, right? So you can remember the mantle is divided into two, upper mantle and lower mantle, and the
Yeah.
lower part of the lower mantle contains some carbon, right? These carbons are under high pressure conditions. So these are found as diamond as there. I mean, originally they are crystallized as diamond, not the conversion of
That.
graphite or organic matter into diamond. It was originally crystallized as a diamond, and these diamond carrying magma is coming up. These magmas are called kimberlites, right? In Africa, you have a lot of kimberlites. These are coming like mantle plumes actually from deep part of the mantle, not as deep as the core mantle boundary, but in the lower part of the lower mantle. So this magma carries the crystallized diamond from that environment. So it is not just,
From the magma itself.
yeah, magma itself. It's not the subduction exactly.
So like when we get a diamond, do we have any way to like classify this is from the like magma and this is from the subduction zone, or is it
Yeah.
like
Actually, the diamond is diamond. I mean, the crystallographic structure is same, but
yeah?
if you study them very detailed, like inclusions, right? Inclusion patterns or inclusion phases there. If you find some
Uh-huh.
silicate inclusions and some fluid inclusions there in diamond, then you can analyze through that to find out their environment, whether it is coming from
Okay.
convection zone or whether it is direct product of a magma, kimberlite.
Lava.
Yeah,
Yeah. Timber.
mainly inclusion-free diamonds can be found from lower mantle. Very, very pure, very nice diamonds.
Okay.
Yeah.
Thank you, sir.
Okay. So I hope you have no more questions. So anyway, if you have any questions, so you can ask next time, or even you can send me an email. So I will attend to that whenever I can get the time. Right. So shall we stop for today now?
Okay. Thank you, sir.
Okay, sir.
Okay.
Thank you, sir.
Thank you, sir.
You're welcome.